Important ones are NASA Outstanding Leadership Medals and the Presidential Rank Award for Meritorious Executive and Distinguished Executive. Please welcome Steve Jerzik to NETS 2019.
Hey, good morning, everybody. It's really good to be here. I'm glad I made it in last night. I'd actually planned, I guess the last time I spoke here was in 2016 in Huntsville. It's unbelievable that it's been 3 years ago, and there's so much that's happened in the last 3 years. I'll just try to catch up where we are with space exploration and how, and then I'll eventually get to technologies, and I'll eventually get to nuclear technologies and how they fit in. So they have to be a little bit patient. But yeah, it's really good to be here. I had intended to spend some time at the conference and see some of the talks, but the 35-day partial government shutdown intervened, and so I'm heading back to DC to do meetings that would have occurred in January, during the end of January during the shutdown. So I'm going to have to keep this talk a little bit shorter than I intended, but hopefully I get it through it in about 25 or 30 minutes. Before I jump in, we obviously had a change in administration a couple of years ago, and when we were preparing at NASA for that change in administration, we were trying to think of how we would articulate the value of NASA to the incoming team. And right away we thought we were going to just dive into missions, right? All the amazing science missions we do, SLS Orion and all our exploration missions, what we do in the International Space Station. And then we stopped and said, we need to back up a little bit and really think about the value not only to the nation but to the world of the activities that we do at NASA across aeronautics research, science, space technology, and human exploration. So came up kind of with 5 core themes. First is innovation and technological breakthroughs, for our missions, to accomplish our missions, but well beyond that. And there's many, many examples of that. New discoveries, that's what science is all about across astrophysics, heliophysics, planetary science, and earth science. And literally the science missions and the research that's done with those missions rewrites textbooks on a regular basis. I mean, it's amazing. I don't know what the number of planets that Kepler had discovered in his lifetime. It's well over 700, maybe even above 800 now. And now we have TESS. And so, not too long ago, we wondered how our planets abundant around other stars in our galaxy. And it turns out, yes, they are. There's a lot of planets out there, and hopefully with James Webb Space Telescope and then follow-on missions, we'll actually get direct images of those planets and multispectral images of the atmosphere. And if we can sense methane, carbon dioxide, oxygen, and CO2 in the atmosphere, there's high probability there's life as we know it, carbon-based life as we know it on that planet. So it's just, I can go on and on about science. That's a whole nother talk. I won't get into that. We support diplomacy and international relations from 1958 on, right? We were birthed out of the Cold War. And then in the 90s, after the fall of the Soviet Union, we partnered with Russia and our other international partners on the International Space Station. And that was a intentional foreign policy decision by the Clinton administration at the time. And it continues to be a great partner. Without the Russians, we actually wouldn't have no way to get crew up and down to the station right now. But we have a launch coming up on Saturday that I'll talk a little bit about later. That's hopefully going to correct that. We contribute to national security. We partner with our other agencies, Department of Defense, Department of Energy, and others, and we contribute to the U.S. industrial base. And finally, and this is one that I try to support in giving talks at many venues, and that's inspiring people across the nation, and particularly inspiring our younger folks. Hopefully we get them in middle school to go into science, technology, engineering, and math. Because if you don't get them by middle school, you kind of lose them in high school. So that's not only in our education programs, but that's a priority for across all our programs. So the first A in NASA is aeronautics. I actually ran a research center for, I ran it for a year, but I was a deputy director for 11 before I got called up to Washington. And I can talk a lot about how aero is transforming aviation. Everything from electric aircraft to enabling unpiloted aerial systems, UASs, UAVs in the national airspace, to urban air mobility. Uber, I don't know if you've heard of Uber Elevate, but Uber has a strategy for what I would call flying taxis or personal air vehicles. And there's another conference in DC coming up led by them, and that's pretty. I commute from down south in Virginia to Washington D.C. every day. I take the train because driving would drive me insane. So being able to use the third dimension and for taxis and commuting, some people call it the Jetsons, would be pretty cool. Okay, so that's a whole nother talk. We'll move on. But the direction that we've been given very clear direction by this administration when it comes to exploration, space exploration, and it's embodied in Space Presidential Directive 1. And I'll read it to you real quick. And I think you'll see a lot of those themes that I articulated earlier about the value of NASA, the nation of the world, embodied in Space Presidential Directive 1. So it says lead an innovative and sustainable, that's a key word, sustainable, right? We're not repeating Apollo. A program of exploration with commercial and international partners, right? So commercial, advancing technological and commercial interests, as well as international partners, engaging our international partners to enable human expansion across the solar system and to bring back to Earth new knowledge and opportunities, beginning with missions beyond low Earth orbit. The United States will lead the return of humans to the moon for long-term exploration utilization. So the moon is a really large focus right now for us, both robotic missions and eventually human missions, followed by human missions to Mars and other destinations. So Mars is the further horizon destination, moon first, and I'll tell you what we plan on accomplishing around and on the moon. Our goals right now are multifaceted. The first one is to transition human spaceflight in low Earth orbit to commercial enterprise. So we want to leverage what we're doing on the International Space Station with respect to technology development, in-space manufacturing, in-space research and development to support emerging markets in the private sector, and that includes tourism too, eventually. So we have stood up a program to do that, and one of the things we've been considering doing for a while now is offering a port on the International Space Station to commercial entities to be able to ring out their research and manufacturing and other in-space activities. But what we'd like to do is eventually end government funding for the International Space Station and be a 20 or 30% user of other commercially operated space stations in low Earth orbit, and then have those stations also be used by other government agencies and the private sector. So that's where we're headed I would say in the mid 20s timeframe. The administration has given us a 2025 kind of deadline to end government funding for the International Space Station. So next we're going, like we like to say, rather than returning to the moon, we're going forward to the moon, right? Because we're doing it in a different way now, a sustainable way, with the ultimate destination being Mars, to enable long duration human spaceflight. And it's going to take a lot of new technologies and capabilities to be able to do that, and I'll go into that later. Again, I can talk about the science portfolio, and I'll talk a little bit about what we're doing in the lunar science program right now. But technology is an enabler for human exploration beyond low Earth orbit. There's no doubt about it, and we need a whole host of new technologies to be able to push human presence out into the solar system both reliably and affordably. Okay, so let's see if I can get the charts to roll. I only have a few of them. Let's see. Oh, clicker. There we go. Okay, so this is not to scale. It's the scale according to emphasis in current policy. Let's just put it that way. So I talked a little bit about ISS and commercial platforms, either commercial capabilities, either leveraging ISS or independent platforms. We're developing the transportation system, the heavy lift system, to get crew and cargo to the moon and beyond. I'll talk a little bit more about that later. That's the SLS launch vehicle and Orion spacecraft. And then you'll see commercial landers. We awarded, I'm trying to remember now, 11 contracts to commercial landed payload services companies, and we're about ready to issue the first delivery order to deliver 80 kilograms of payload to the surface of the moon. I'll talk a little bit about the gateway and where we are at the gateway and how the gateway is important for a couple of reasons, many reasons, a couple being it allows sustainable exploration and reusable systems. It's kind of like a reusable command module. It also allows us to demonstrate technologies and capabilities to push out of the Earth's moon systems. And there'll be other surface missions. And then our robotic missions on Mars, and we'll continue those. I'll talk a little bit about that. Okay, I'm going to skip this part to keep it a little short. Sorry about that. Need a little music in this part of it. Okay, so talked a little bit about low Earth orbit and transitioning station to commercial capabilities in the 2020 timeframe. We're still going to need the station. It is critical. One of the critical things that we do on station is research to mitigate the effects of long-term spaceflight on the human body. We're finding things out every month and every year. The vision problem just cropped up probably about a year and a half ago, and we still haven't actually nailed down exactly what that is. It could be a couple of different phenomena. Muscle wasting and bone mass loss, we've kind of tackled that through exercise and exercise equipment on station. However, we're going to have to figure out how to shrink those systems down for transhabitation when we push out of low Earth orbit. We develop and demonstrate technologies. One of the critical technologies that I won't go too much into here is more reliable, higher performance environment control and life support system technologies. We're closing the loop on water pretty well, on air not so much yet, on recovering oxygen from the atmosphere, and we're working on technologies to do that. And then the systems break down all the time on station, and we have spares, right? And we have crews to repair. For long duration missions, we can't spare everything like we do on station, so we're going to have to improve reliability. Commercial research and development of products and services. I know pharmaceutical industry, manufacturing, and other industries. And so just some examples of what we do on station. So again, we want to enable a sustained presence on the moon with robots and people. We want to enable crewed missions back to the moon and around the moon and on the surface. We want to provide capabilities to do science, not only lunar science, but other science, maybe astrophysics and heliophysics and even earth science. We need to demonstrate technologies to enable capabilities, not only for sustained presence on the moon, but also to push onto Mars. And we want to, so it becomes the moon kind of becomes the proving ground for capabilities and technologies for Mars. So again, we're going to start with robotic precursor missions for science and technology demonstration, as well as eventually resource processing. We're starting with CLPS, the Commercial Lander Payload Services. We actually just selected a set of payloads that are being developed at the NASA centers internally in parallel with going out with an announcement for payloads to go on those landers from universities and industry. So I think we selected maybe 4 or so technology payloads and more than a handful of science payloads. And we have a goal of having the first landing by the end of this calendar year. I don't know if that's doable. We're challenging our industry partners to do that. But if not by the end of this calendar year, early next year. And the idea with CLPS is take more risk. Lower cost missions of smaller landers, more shots on goal. Some will score, some will not. We'll learn and we'll move on. So we want to take more risk with these small lander missions. SLS and Orion, the crew module and the service module are now, European service module are now integrated down at Kennedy Space Center, and we did first powered on testing. So we've got over a year worth of integrated performance and environmental testing on Orion before it's ready for the first uncrewed flight in 2020. And then the core stage for SLS is coming together down at the machine assembly facility. That's pretty much the last element of SLS that needs to be complete manufacturing. Everything else is pretty much, all the other elements, the boosters and tankage and everything are ready to go. And so hopefully, again, in 2022, we'll have the first crewed flight test, and either late 22 or early 23, we'll have the first crewed flight of Orion and SLS to the moon. So the gateway, again, we have multiple activities going on to develop elements of the gateway. We released a request for proposal and got proposals in for the power and propulsion element, what we call the PPE. And one of the features of that element is to demonstrate high power solar electric propulsion. So we developed 15 kilowatt or so thrusters with our industry partners Aerojet Rocketdyne, and we will have 3 active strings and probably 1 spare on the PPE and demonstrate a 45 kilowatt solar electric propulsion system. A logistics module is key, as well as an airlock, and then a habitation module. And on the habitation module, we're going to build on what we've done with the next step BAAs in having multiple industry partners prototype habitation modules, and we're testing them at either Johnson, Marshall, or Kennedy, and then we'll release the request for developing the habitation module flight system for the PP. And again, it's going to be in a fairly high lunar orbit. It allows us to get it'll provide staging for crewed missions to go. So Orion will go to the gateway, and then a lander will take crew down to the surface and back up again. It'll allow reusability, and at least initially, of the ascent module, and eventually, hopefully, of the descent module. And it also allows access to anywhere on the surface and communications, really effective communications coverage on the lunar surface. And then we just released a request for proposals for or BAA for human class lander studies. So right now the architecture has the landing system in three elements. There's the descent stage, there's a ascent stage, which will, the crew will be able to go down and stay on the surface for about a week and return to the gateway. And then there's a tug that takes the ascent vehicle and descent vehicle down to a low lunar orbit, and then descend from there. So that's our current architecture. We're also open to other options and other approaches, but that's kind of how we would go use the stage at the gateway, go through the gateway and down to the surface. On Mars, we continue our precursor missions. We are the only country that successfully landed something on Mars. That's landed something on Mars that actually worked after it landed. So it's really, Mars has a poor excuse for an atmosphere, so it doesn't really slow you down very much. But you have to still worry about, you're coming in at a very high speed, and you still have to worry about air heating and aerodynamics, and then you're on chute for some period of time. We use the supersonic parachute that we used, starting in Viking, and then with Mars Science Lab or Curiosity, and now Mars 2020, we have the Sky Crane for the terminal ascent part of the mission. But InSight's on the surface right now, and it landed successfully back in November, and it's a more like a geology mission. It's going to detect earthquakes or Marsquakes, and drill down in and take core samples drill down about 5 meters and take core samples of the Martian planet. And then our next rover mission will be 2020, and I'll talk a little bit about some of the tech we're demonstrating on Mars 2020 a little bit later. So innovation and technology development is key to enable all of what we do, or both robotic missions and human exploration. So just some examples. Particularly on CLIPS, we plan on demonstrating precision landing and hazard avoidance technology using Doppler LiDAR technology and other sensors, cameras. For the first time, we're not going to fly blind. We're not going to fly down to the surface of Mars blind on Mars 2020. We're going to have a camera that's going to get real-time video imagery, and we're going to use something called terrain relative navigation, where we compare the real-time video with 3D elevation maps of the surface and look for hazards, right? Rocks, slopes, very sharp slopes. And if we're headed to a dangerous landing spot, we can command the engines on the powered descent vehicle to divert and avoid that hazard. So that's allowing us to go to places on Mars that would be too risky if we were just flying blind down the surface. We have this like 10 by 15 kilometer ellipse that we land in with some probability, I guess 2 or 3 sigma probability or so. Well, we're trying to get that down to a 100-meter circle, right? So this will allow us to pick the spot in that ellipse that we land on, and avoid dangerous places. It turns out some of the more scientifically interesting places are more dangerous to land, and so that'll let us do that. We're going to demonstrate satellite servicing using robotics to be able to refuel satellites, repair satellites, and that'll be key for reusability of things like the ascent vehicle for getting from the gateway down to the moon and back. In situ resource utilization is also going to be important. There's a lot of water on the moon, particularly in the permanently shattered craters. We want to send a rover down into those craters and look at how the water is bound with the lunar regolith and how difficult or easy it would be to extract it, process it for fuel, water, and other things. So, that's something we do, and that I'll talk about this a little bit later, but that drives power, particularly on the surface, to have that excavation equipment and plant to process the water out of the regolith. On Mars 2020, in addition to terrain relative navigation, we're also going to have an experiment called MOXIE, which is going to demonstrate generating oxygen from atmospheric CO2 at very low volumes. So that's atmospheric ISRU on Mars. So that's going to fly on Mars 2020. Okay, so let's talk a little bit about power. So we definitely have increased solar power by both improved efficiency in solar cells and large deployable structures to get just larger acreage, and you'll see that on the power and propulsion element. However, we also continue to use radioisotope power systems. We have one on Curiosity and RPS. We'll have an RPS on 2020 also, and we're doing work in both improving the conversion efficiency of thermoelectrics, as well as what we call active conversion, either using Stirling cycle or Brayton cycle systems. And so we'll continue to do that work to kind of extend the capabilities of RPSs. But when you start to get to a kilowatt or so, now you're talking about multiple RPSs in parallel, and you want to probably go to fission-based system. I'll talk a little bit about that. Nuclear surface power. So when was the kilopower demonstration? Two years ago? March. Yeah, March of last year? Oh, so it was only a year ago. Man, time is just warped for me. So got to go to the Nevada Nuclear Security Site and witness the kilopower demonstration, which is basically a reactor, a heat transfer system, and a Stirling cycle engine to generate 1 kilowatt of electrical power from 4 kilowatts of heat from the reactor, energy from the reactor. Very successful demonstration, something we've been trying to do for many, many years. Yeah, you guys told me. Really focused on the demonstration and not new technology, new reactor design, but really integrating the reactor with the heat transfer system, the heat pipe system, and the energy conversion. What we'd like to do is demonstrate a system on that order, or maybe even of higher power, on the moon, and land a system on the moon, and then hopefully utilize that system on the moon to operate surface systems, including our ISRU systems. There's also been many studies. We don't have anything focused and active going in this area, but there've been many studies on what you could do with kilowatts of power for deep space missions and fission-based missions, particularly enabling, I also call active remote sensing, radar and LiDAR. The things that we do in Earth orbit with solar power that we can't do very well at the powers that we can generate with radioisotope power systems. And then there's propulsion. And propulsion is one of those areas where we really haven't had a breakthrough in a while, right? Chemical propulsion is chemical propulsion, right? It's going to have a certain ISP and a certain thrust level, and that's pretty much it. It served us well for many years. Like I talked about the super efficient, the high, like 2,500 to 3,000 ISP, electropropulsion. We have a couple efforts going on. One in nuclear thermal propulsion, where we're developing a reactor design and trying to prototype that reactor. And I think, I always get, when I talk about nuclear thermal propulsion, the folks that have been around for a while kind of snicker, right? Nuclear thermal propulsion, we had NERV in the 60s, we dropped it didn't go anywhere. And my response to them is, well, technology has advanced a little bit since the 1960s. And I think we're using those technologies and innovating in nuclear thermal propulsion. Some of those technologies are physics-based modeling, right, and neutronics, computational capabilities to run those models that we couldn't even dreamed of. They're in our pocket now, right, that we couldn't even dreamed of back then in the 60s. Materials, right, advances in materials. One that kind of surprises me a little bit for this is additive manufacturing, 3D printing, and 3D printing advanced materials. That's a game changer for our industry in general, but for this more specifically. And then things like autonomy and autonomous systems to be able to operate these systems safely. So again, like a lot of things, innovation is the integration of technologies and inventions to deliver a new capability, like high thrust propulsion capability, like nuclear propulsion. And then I think Franklin Shane Diaz spoke yesterday, and you probably talked a little bit about Vasmir. So just a little. So we are funding two, I would call, one very high more standard electrical propulsion approach. It's a 100 kilowatt thruster. But then there's Vasmir and another effort we're funding that would enable nuclear electric propulsion. And so we're trying to get to kind of a steady state demonstration test there, and then if it pans out, we'll start looking at what the reactors look like to power those systems, because things like Vasmir, they really don't pay off from a efficiency standpoint until you get to the megawatt class type systems. So let's see. Oh, got the clicker. So this is a very famous picture, right? The moon, the Earth from the moon. So again, we're going back, or we're going forward to the moon, right? We're going to establish a sustained presence around the moon and on the moon. We're going to exploit the resources on the moon. We're going to develop technologies, improve our capabilities on the moon that will then take us beyond the Earth-Moon system and hopefully onto Mars someday. It's more like the Antarctic model, where we're going to build up capability over time and build up the ability to do exploration and science over time, as we do our about 1 year, one crewed mission a year type cadence. You know, I was riding the train into work today, and I was thinking, you know, I don't have a lot of career left at NASA. I'm in my 30th year at NASA, so I'm thinking, one of the small number of things I want to accomplish before I leave NASA, and one is to set the NASA and the nation on a sustainable course for human exploration. I mean, if we can set a course that transcends administrations and other political whims, that would be just a huge win for the agency, the nation, and the world. And then this picture is interesting. So this is Earth and the Moon from Mars orbit. So, you know, someday, hopefully, there'll be a person on, or persons on the surface of Mars taking this picture versus a robotic probe. So I'd like to end with a couple of quotes. The first quote is from a former NASA Associate Administrator, Arnie Aldrich, from 1990. And it's about Mars. So Mars responds to a fundamental need in all of us. There is a human imperative to explore. People must explore because they are human beings with a desire to expand the scope of human experience. Exploration adds to our knowledge, satisfies our curiosity, and responds to our sense of adventure. We're going to Mars because we are alive, and because it reflects something very special inside each and every one of us. And then the other quote is from a famous author that probably most of you know, James Mitchell, wrote many famous books. And his quote is, "There are moments in history when challenges occur of such a compelling nature that to miss them is to miss the whole meaning of an entire epoch. Space is such a challenge." So thank you for the opportunity to speak with you today. I'm sorry I couldn't spend more time with you and see some talks and interact more, but have a great rest of the conference, and hopefully the weather will cooperate. Thank you.
Please join me in thanking Steve for making the time here as he scurries out of the room to get back to the budget and other wars in Washington, D.C. So we will take a break here for coffee as we reconfigure now for these lightning talks in the next session. Take a look at the program. It is as accurate as we can make it. There will be no discussion, heads up, no discussion after lightning talks, so it's make your points, do your talk, and then you can talk to the people that present later on the day and tomorrow. So thank you very much.